We have the third presentation by Otto, and today's talks is maybe with the topic that most associate with Otto. It's the lock-in thermography. So, Otto, the stage is yours. Thank you very much again for your visit. It was great to have you here.
Yes, it also was great for me to be here, and thank you very much for the invitation to come here. Yes, this will be the talk about special investigation techniques of lock-in thermography. So this will be not an introduction to lock-in thermography. For an introduction into this topic, please have a look at my book Lock-in Thermography, which will see a third edition, by the way, this year or at the beginning of next year. So in this talk, after some introduction, I will go a little more into the details of the so-called local I-V method, which I have mentioned already in my first talk on inhomogeneities. Then I will report about illuminated lock-in thermography, so-called ILIT-based local efficiency analysis. Moreover, I will report about the possibility to image short-circuit current densities via lock-in thermography. There are two possible techniques, and will introduce a new method for depth dependence investigations. This is a brand new results. At the bottom you will see some of the results which you're going to see in this talk. So, as I made clear already in my first talk, dark lock-in thermography, which I will abbreviate here DLIT, is a technique of choice for shunt imaging. However, lock-in thermography can do much more on solar cells. And the point is that these results can easily be quantified in terms of local current densities, which is used in the so-called local I-V method, which I've mentioned already before. And the locally contributing efficiency in a cell can alternatively be imaged directly under realistic imaging, so illumination conditions by illuminated lock-in thermography, and even, as I mentioned, the short-circuit current density can be imaged. And moreover, recently we have developed a new method for distinguishing heat sources in different depths of a solar cell. In this talk, these methods will be introduced. Now, let us come to more details of the local I-V method. As I have mentioned already before, dark lock-in thermography can be interpreted so the signal is directly proportional to the locally dissipated power density, and this means for a given applied voltage to the locally flowing current density. And this is a so-called two-diode model here, which I have shown already in my first talk. This is the first diode, which describes recombination in the bulk and at the back surface. This is the second diode, so-called, which describes recombination in the depletion region, in the PN junction. This is ohmic shunting, and here the short-circuit current density. So this is written for illuminated conditions. And I must say, also lock-in thermography, and also in particular this local I-V method, is based on the model of independent diodes, which is for each pixel, it's sketched here. So we assume that each pixel has a series resistance to the terminal and a parallel resistance to diodes and the current source. So, and the results of this procedure, then the procedure itself consists in performing up to four measurements for 3 forward biases and for 1 reverse bias. And with these 4 measurements, we can fit for each pixel separately these 4 parameters, J01, J02, N2, that's the ideality factor of the depletion region recombination, and the ohmic conductivity, which is the inverse of the parallel resistance. Yeah? The ideality factor of the first diode is assumed to be homogeneous, but can be chosen to be larger than unity for considering injection-dependent lifetimes. So the local series resistance or the local diode voltage must be known. This can be done from PL or EL analysis, as I will show below. And after these local diode parameters are known, the software calculates images of the local cell parameters. I have noticed some of them here. I must say this software is commercially available. So now let me demonstrate. This is a typical example. That's a standard technology solar cell, and here these are the input images which have been evaluated, measured at 0.5, 0.55 and 0.6 volt and at -1 volt. So we must be here, we have to apply a low reverse bias in order not to come already in some carrier multiplication regime. So already here you see the images differ from each other. At the highest voltage we have a nearly homogeneous, except of some outrunning, so that's the so-called J01 shunts. And at low voltage, the J02 current is dominating, and also ohmic currents are dominating. And here we have an electroluminescence image of the same cell. And if we evaluate two such electroluminescence images, we can obtain an image of the local diode voltage, as I've explained in my second talk. And this is this, and this shows, for example, now here broken grid lines and these typical things. And from this local diode voltage and the current image, so this is at 0.6, this is also at 0.6, well, and this current density image, the so-called Resi series resistance, can be measured according to a method proposed by Klaus Ramsbeck at ISFH in Hameln in 2007 already. So, and if we have measured this we fit all the pixels to this two-diode model, and the result are these parameter images, J01. J02 itself is not useful to be displayed if the ideality factor is considered as a variable, because the regions of high J02 also have a high ideality factor, and this makes J02 even larger. So J02 spreads over many orders of magnitude. Therefore here I've shown the logarithm of J02, and it goes 10 to the minus 8 to 10 to the minus 2 amps per square centimeter. And the ideality factor, so blue means ideality factor 2, as you, according to standard theory, as you would expect it for a diode. But you see in the regions where we have these shunts, these J02 shunts, it is much larger than 2. It goes up to 10 here in these two dominating shunts. So, and when we have this, we may construct both dark and illuminated I-V characteristics in these special positions. So position A is a typical J02 shunt. Position B is a J01 shunt, so a maximum of the J02. Position C, I have to go back, is a very good region, as you will see at the end. And position D is an ohmic shunt. I haven't used these ohmic shunts because they have ohmic and J02 contribution, but this is a pure ohmic shunt, a weak one. Okay, and already here from these characteristics, you see that these regions, they differ substantially from each other. The black spots are the measured points, and the lines are according to the two-diode model, the simulated characteristics, and you can distinguish them nicely from each other. So if you have all these parameters, you can calculate local efficiency parameter, for example, VOC. This is all under the assumption that the pixels are electrically separated from each other, so-called potential or expectation values. And then this can be done with different illumination, assuming different illumination intensities. And we see, for example, this point D, which is the weak ohmic shunt, is practically invisible in the VOC image at 1 sun, but it is visible at 0.2 suns. Nicely, you see? And at the fill factor at 1 sun, it is visible. So which shows again that ohmic shunts are first degrading the fill factor, and even if they are stronger, they degrade also VOC. So the inhomogeneities of the series resistance only influence the fill factor as expected, and not the other parameters. And yes, and the good region C here, there we expect the best possible efficiency. So this can be done here. And also, if we sum up across all pixels in the image, then we may simulate global characteristics, both dark and illuminated. And as you see here, they agree very well with measured characteristics. And even here in the region where we have not measured, even here, so it is correct, because we have chosen the ideality factor N2 which dominates this current here as a variable. So this is much larger than 2 here. And also the illuminated characteristic nicely agrees. We have to expand the axis here to see anything. What you see here is that the fill factor that's simulated is a little higher. And this you also see here in this table. So maybe this is interesting. So here these are the intensity dependence of the efficiency in all these regions. And clearly we see region C, the best region is the best. The whole cell performs not much worse, a little worse, but also the intensity dependence is nearly the same. This is because J01 is dominating. But here, this J02 shunt, and in particular in the position of the ohmic shunt, the efficiency drops down substantially with reduced intensity. And here are measured versus simulated data, and you see the agreement is quite well. In particular, if we look, so the agreement between simulation, producer data, and we also have measured the illuminated characteristic cell using 850 nanometer illumination, and this agrees quite well. And if we simulate the best region, then we see that the VOC can be substantially higher, and also the efficiency could be substantially higher than measured and simulated if we could get rid of these defect regions. This was already explained in the first talk. Now let me just demonstrate the so-called cut shunt option. I have measured already in my, I have explained already in my first talk that we have the possibility, if we have all data of the cell, then we can highlight some region containing some shunt, and we replace the properties of this region by that of the surrounding. And so virtually cut out the shunt. If we do this with all the ohmic shunts here, we end up here. So all ohmic shunts are cut. These are J02 shunts, which I have not cut. And if you compare the illuminated characteristics here, this looks much better than this one. And again, here we have fill factor improvement and an improvement in particular also of the efficiency due to these shunts. This was reported also already in the last in the first talk. I just shown you how it's being done. So let me summarize the local I-V method. This available method allows to perform a quantitative local efficiency analysis of solar cells. And the obtained local efficiency parameters allow to judge about the influence of different defect types on solar cell parameters. So the possibility to evaluate selected regions, for example, cell edge, or cell without the edge, or the best region of the cell, gives quantitative information on the influence of these regions on the efficiency. And in particular, the cut shunt onion option allows to judge the influence of single shunts on the efficiency. And this method is used already in various PV labs. I have named a number of them. UNSW is still missing, but I hope in future you also will have this method available. Okay, now this brings me to the second story, dark versus illuminated log-in thermography based local efficiency analysis. It was proposed already in 2008 by Klaus Ramsbeck at Institute of Solar Research in Hameln in Germany to use also illuminated log-in thermography for efficiency imaging. And this method, the argument was this method is performed under realistic illumination conditions at MPP, yes, and does not assume any solar cell model, yes. And originally, this method was restricted to measure only internal, which means reflection corrected, and irradiation intensity independent monochromatic efficiencies. However, we recently have extended this method to measure also external and also AM 1.5 efficiency. This was published last year. Okay, let me explain the difference between efficiency potential and in-circuit efficiency once again. So the efficiency for the efficiency potential, it is assumed that each pixel is electrically isolated from the surroundings. So we have the parameters of this pixel and assume that it's an own solar cell. Yeah? This definition needs a solar cell model, for example, 1 or 2 diode model. And for example, the local efficiency potential is always positive. So even if you have a strong shunt, if you illuminate it, you still have a positive voltage there and some photocurrent, even if it is low. And the efficiency potential parameters in position xy mean that an extended cell showing the parameters of this position would have these parameters. That's the meaning of efficiency potential. On the other hand, the in-circuit efficiency describes the locally contributing efficiency if the cell, as it is at its VMPP, at its maximum power point voltage. So this is defined as VMPP of the cell times local current density divided by the illumination power density. And so here the in-circuit VOC is actually the local diode voltage if the cell is at its VOC. So as I have written here. So in inhomogeneous cells, local variations of the VOC potential are always much larger than that of VOC. I will demonstrate it below. And these in-circuit definitions, they don't need a cell model. And the in-circuit efficiency may become negative in shunt positions because then here this current, this is counted positive now for photocurrent, and if the dark current dominates, this becomes negative and then also the efficiency becomes negative. So the basic ideas of the Ramm-Spec method are the following. At a short circuit condition, the complete locally irradiated power density, actually the absorbed power density, is internally converted into heat. So at maximum power point, some fraction of the irradiated power is converted into electric energy and fed away. Therefore, the local heating becomes correspondingly low, and we can say the electrically generated power density locally is proportional factor C times the difference between JSC ILIT and MPP ILIT. That's the basic idea. And I have to explain there's a difference between external and internal efficiency. External means referred to the irradiated light, and internal means referred to the absorbed light. This is similar as for external and internal quantum efficiency. So the absorbed power density is this constant times ILIT at short circuit. And so the basic idea of basic formula actually of Ramm-Spec was that this internal and in-circuit efficiency is this here, ILIT JSC minus MPP divided by ILIT JSC. This magnitude refers to the irradiated wavelengths. So it's a monochromatic efficiency, which is higher than the AM 1.5. And it is independent of the irradiation intensity because both it is here in the numerator and the denominator. Okay, we have proposed some extensions. So, for example, we have proposed to measure C directly by DLIT. So this is just evaluate the average DLIT signal of the whole cell, where we know the dissipated power, it's IV dark, yes, and this leads us to this simple equation for the in-circuit external efficiency. Here for the illumination intensity directly 100 milliwatt per square centimeter, as for IM 1.5 can be assumed and can be and regarding we also have developed a formula. I cannot go into all details for the internal in-circuit. This is the external, and this would be the internal in-circuit. Here also reduced efficiency, which is given here by the parameter shunts, can be regarded. Okay, so for details, I always have written here these original publications. For details, please have a look at them. So now what comes out? We have the same the same cell, with this shunted cell, which I have shown below, and these are DLIT results. So we see, in spite of the shunts, we can obtain a J01 image, and also the J02 type current can be displayed separately, and this is the ohmic current, which is quite strong here. And now we have here the efficiency potential, the VOC potential. This is this resi RS, as I have explained it before. And these are the in-circuit data. The in-circuit efficiency at the first view looks similarly than the efficiency potential. However, looking careful, this is black, whereas this is blue. And if we scale this not from 0 to 22%, but from minus 50 to 22%, we still see here some dark spots, which means in these ohmic shunts, the efficiency, the in-circuit efficiency is negative as expected. Yeah? And also we nicely see here that the inserted VOC has much lower variations than the VOC potential as we already expected. The reason is the interconnection of all these regions in a solar cell by the grid and by the emitter. Okay, and these are some typical results. Here we see the DLIT efficiency. We only can compare in-circuit external efficiencies because DLIT can only provide external efficiencies or predict. And we see it's practically the same. We see some small deviations. For example, here this reddish color is not explained, not seen here. And also looking more carefully, so for example, these defects are coming something stronger here than there. It is not very clear yet where these differences come from. They may come from an inhomogeneous illumination intensity, or maybe also that in this evaluation Peltier effects are not considered yet. Maybe they should. So, well, this was this story. Now comes the next story, which is JSC imaging of the short circuit current density. This is also a very important local solar cell parameter. And usually it is imaged by light beam induced current, LBIC, so-called LBIC. However, LBIC is available as a rule only monochromatically. So you have it for only one wavelength, and for getting AM 1.5, so typical solar spectrum results, you need several wavelengths, and then you may construct it. However, this is not always available. So, for example, the Loana PV, by PV tools can do this. And on the other hand, the average JSC is usually available from Fleischer ISC data, where these are the solar cell, the global solar cell data. And so if you don't have LBIC, you can get the short circuit density distribution by ILIT-based JST imaging. And there are two methods available. One is ILIT-based and the other one is DLIT-based. So illuminated and dark log intermography. Let us start with the illuminated log intermography-based JSC imaging. This was not invented by us, but by Fabian Fertig at Fraunhofer-ISE. And it goes like this. So we have a weak reverse bias to our solar cell and illuminate it. And then, I mean, the currents flowing there, this is actually the short circuit. So the short circuit, the current under short circuit and under weak reverse bias is the same. And here we have a certain current density. And here the electrons lose their energy. And so the heat generation of these electrons is the short circuit current density multiplied by reverse bias plus barrier height at 0 volt. Yes, and so the technique goes like this. We have continuous illumination. The bias is pulsed between 0 and -1 volt, and then the resulting ILIT signal is proportional to the short circuit current heat. All other heat sources, they average out by this log-in method. It must be said that local emissivity correction should be used, as the authors claim. And if there are ohmic shunts, a corresponding dark log in thermography signal taking under the same biasing conditions has to be subtracted. And then we get a signal which is at least proportional to JSC. And the absolute scaling occurs finally by fitting the result to Fleischer ISC data, and that's a typical result taken from this publication. So here we see the LBIC JSC. Here we see the ILIT JSC with shunt correction. Here this is without the shunt correction, and you see these bright spots. These are some ohmic shunts which can be, however, corrected. Of course, you see the spatial resolution of this technique is much worse than for Albig. So, and if you don't have illuminated log in thermography, you also can do it with dark log in thermography, and the physics behind is completely different. So this method is based on the fact that J01 is a measure of the bulk recombination property. And this also holds for JSC condition. And moreover, we can assume that the generated current density, so all absorbed photons, assuming that each photon absorbs one electron or generates one electron, and the current density by these should be homogeneous. Well, if the absorbed light is homogeneous. And then JSC equals this generated current density, which is a constant, minus the local recombination loss. Yeah? And here we have simulated by PC1D these generation losses for two cases. That's for a standard cell, that's for a PERC cell. And here the parameter is the illumination wavelength. Of course, this depends on the wavelength. And also for AM 1.5, we have calculated this, and some curves come out. And we have found that these curves can be approximated by this simple formula, having two parameters A and B. Yeah? And regarding the measured values and mean value of JSC, this leads to this relatively simple formula that the local JSC is the average of the JSC minus this current loss, and plus a correction factor which serves that then the average of JSC is again this one. So, and here we see such a typical result here. JSC as a function of J01. And if we apply this to a standard technology solar cell, we come to this. That's Albig JSC. And if we artificially blur this Albig JSC, we come to this image here. And this is our DLIT JSC, which is based on this DLIT-based J01 image here. And if we draw, I mean, you see the results are not exactly the same, but are quite similar. And if we plot the DLIT JSC over the blurred, so the scatter plot here, then we see it is nicely proportional. We also have done EBIC J01, but I will not go into this detail here now. Instead, let me introduce the last technique I wanted to show here, which is a new DLIT method for depth-dependent investigation. That often has been asked, isn't it possible with log-in thermography to distinguish between recombination, say, in the emitter and at the back contact? And until now, I always said it's not possible because a silicon cell can be considered to be thermally thin. So its thickness is only 180 microns. However, the thermal diffusion length, which is actually the length where the thermal waves can spread, it is 1.7 millimeters. So it's a multifold of that. And therefore, the temperature modulation at the top and at the bottom of the cell is nearly the same. However, in non-destructive testing and integrated circuit failure analysis, where also log-in thermography is widely used, there is a method. The depth of a fault can be estimated by considering the phase of the lit signal at the surface. And this is being done here on these multi-chip devices. For example, storage devices, memories, yes, they are often the active layer of an integrated circuit is only a few microns thick, so then they thin it to, let us say, 20 microns per chip, and then they glue several of these chips on top of each other with some glue in between. And here you can, and then in addition, you often have a mold compound where everything is molded together. And then if you have a local heat source here in one of these so-called dies, so the IC people, they call the chips die. And then you can calculate the phase shift of the thermal signal arriving at the surface as a function of the log-in frequency for all of these dies, for all of these depths. And you see some curves coming out, and these are measured points, and we see in this case the heat source was in die number 1, which is here the uppermost one. So this works. Can this also be made working on solar cells? Hardly. I say, so here I have calculated, so we use a nice similar, a nice software for modeling these solar cells, which is called DConf, which is also available. And with this, I could simulate the phase as a function of the source depths and also the in-phase signal. So for a thermally thin, for an ideal thermally thin sample, actually the phase should be minus 90 degrees, and the in-phase signal as a 0 degree should be 0. In reality, you see, it depends slightly on the depths, but the variations here are much below the typical variations of the phase and also of the in-phase signal across a typical solar cell. They are a factor of 10 to 100 higher. So directly it cannot be measured. However, it can be measured if we make the front minus back difference between these signals. So we have to blacken the surface on top and on bottom, that we are sure that what we see with the infrared camera is just the temperature modulation of this surface. And then we measure it from both sides, turn it around, and then we try to align these images and yield the difference. And these are simulations of this. So here, this was a heat source at the bottom, and this was at the top. And also with the phase, it should work, yes. And interestingly, these difference images, they are not blurred. So the input images, I don't show them here, but in the original work, they are shown. Meanwhile, this work has appeared. It's not in print anymore. So the input images are both blurred, the difference images are not blurred. And this is because they come from only vertical heat diffusion and through a thin crystal. So there's a first experimental verification of this method. So here the imaged region is close to the edge of a solar cell. And here we have a bus bar, yes, and below the bus bar is the silver back contact. This was a standard technology cell, and we know that the silver back contact has a high recombination velocity, so it represents a heat source at the lower surface of a solar cell. And here, that's the edge of the cell, and here we have made a scratch on the solar cell through the emitter, which represents a heat source at the top of the solar cell. And so this and that, this at the bottom, here at the top, and these are the results. That's the phase image itself and the in-phase image itself. And well, I mean, here both heat sources are appearing a little brighter than the background because these are heat sources, and here we have less heat sources. However, in the phase different and also in the 0 degree difference images, we see actually what we wanted to see, so that the heat source at the bottom appears indeed dark, and in both cases, and this appears bright. Here we have some artifacts. For example, here this dark signal at the left and here at the right. It is due to that the angle of the two images was not exactly the same. So it is very critical to align these images to each other. And here we didn't have the possibility to correct the angle. And also we have some residual blurring here. And I believe this is due to the fact that our black layer was not exactly the same at the top and at the bottom. But nevertheless, it can be taken as a proof of concept. Well, and now let me remind you. So my starting point was that log-in thermography, which is often used only for imaging shunts, and indeed for shunt imaging, this is the method of choice, the best possible method. However, as I have told at the beginning, it can do much more, which is summarized here. It can be done ideality factor mapping, for example, which is contained in local I-V. I have shown ideality factor images here. And it can make efficiency imaging by also illuminated lock-in thermography, as I've shown here as well. What I haven't shown was it can be used to image breakdown parameters, but I-V slope, I-V temperature coefficient and avalanche multiplication factor, I have shown an example of this in my first talk considering regarding the inhomogeneities. What I haven't shown is it can directly image breakdown voltage. Just images at certain reverse biases are made, and where then so these breakdown sites are appearing, this voltage can be monitored. I have shown here JSC mapping, and what I haven't shown here is imaging of Peltier effects. This is also nicely possible. Even Peltier coefficients can be measured quantitatively. And also what I haven't mentioned here is this Carrier density imaging or infrared lifetime mapping, what is the same. Lifetime mapping on wafers, which also can be performed by illuminated lock-in thermographies. You see the references to all this here. So this brings me to my conclusions. I hope that I could show that lock-in thermography is more than qualitative shunt imaging. And by using this local I-V method, so DLIT images can be evaluated quantitatively, and this leads to realistic local modeling of inhomogeneous solar cells, and the influence of local defects on the efficiency can be evaluated and quantified. So the results may be cross-checked by illuminated lock-in thermography-based efficiency imaging, which needs no cell model. However, it has other limitations. Also, JSC can be imaged quantitatively both by dark and illuminated lock-in thermography, and there is a new proposal to perform even depth-dependent DLIT investigations, hence to judge whether a heat source is at the top or at the bottom of the cell. However, this method still has to be improved. There are many further options for lock-in thermography, and I'm sure that some more will be invented in future, and I'm looking forward also here to contributions from UNSW. And this brings me to the acknowledgement. I thank for financial support. I thank also for my colleagues. My last colleagues were Jan Bauer and Felix Frühauf. And many thanks in particular to the company Infratech, located in Dresden, Germany, who have provided and further developed the LIT system used for these investigations. And I thank you for your attention. Thank you very much.
Thank you so much, Otto. It's quite amazing what you can do with this technology. We definitely need to get as well. Questions?
Everything is clear? There's one.
I'll ask you a question about the instrumentation.
Yes.
So in order to make these measurements, what sort of optics and camera do you have?
Well, I mean, the camera is an indium antimonide detector. Our camera, and that's actually the optimum camera today, is 640 times 512 pixels. And it has a frame rate up to 300 hertz. So we have been using 200 hertz here. So it is quite good. That's actually the optimum you can do at the moment. And it's not so easy to establish this system by yourself because of the synchronizing necessity. So as a rule, you use an industrial system. So it's easier to use an industrial system than to establish it by yourself.
Other questions? That's the case. Let's thanks Otto again, and thank you again for the visit, Otto.
Yes, and thank you again for your invitation.